Hi, everybody. I'm glad to follow Riley because our talks are actually related. I'm also going to talk today about making a responsive web map. Mine isn't starting off as a print map, but we ran into some of the same issues. I'm defining a responsive map as one web map that's coded to adjust itself, so it can be used well whether it's accessed from desktop or tablet or mobile. And the map I'm going to show you today is built with CARTO.js, but these issues and solutions we're going to see apply to responsive maps made with other tools also. Because whichever tool you're using, designing responsive maps well can require more than just resizing for different screens like Riley was just demonstrating also. So the first set of tips is about handling the map's data efficiently. Like with any web map, the first step usually involves cleaning the data and importing it to a database. In the links at the bottom, I wrote some example code snippets you can use for cleaning your data if you're keeping it in a Postgres database. And if you do happen to be working with CARTO, the second one is for importing your data if you're working with a large data set. But what I really wanted to show you here are query optimization tips once your data is already imported and cleaned, because these can help your web map render better. Web map tiles, at least at CARTO, are made from a Postgres query that retrieves data, which then gets styled. And depending on the query you're using or how much data you're working with, sometimes this process can perform slowly, which means your map can take a while to load. So these are some methods that we found are helpful to speed the queries up. The first one is to create indexes. So indexes in Postgres can be thought of just like the index in the back of a book. You're creating an index for a column in your data set, and that enables the column's data to be found more quickly when it's used in a query. Clustering reorders a table based on the index of one of its columns. So for example, if you have a string column of categories with an index, clustering rearranges your data so that rows that have the same category are grouped together. If you open your data set, you wouldn't see this though, because this is happening at the database level. It's not affecting the way that the retrieved data is shown to you. So I've put these tips and some other ones in that data optimization link at the bottom. But now I'm going to move on to design. So once you have your data ready, you can move on to what I think is the more fun part. In responsive maps, there are two pieces to design. So there's interface design and there's cartography. Because in addition to visualizing the data, when you start to think about how your audience can view and interact with it on small screens, there are a few problems that are specific to maps that you'll need to design a solution for. Some of these might be familiar to you from Robin Solachko's talk from last year. She did a really good job of covering these common issues we're going to see and some more, so I encourage you to find her 15 conventions of web typography slides online. But when I was building the prototype, I'm going to show you the first of these kind of common problems that I found was accidentally scrolling the map. So picture reading a news article with a full-width map in it. When you put your thumb on the site to scroll it vertically and your thumb hits the map, it can accidentally drag the map or accidentally zoom it, and you can actually get stuck and not be able to reach the bottom of the page or read the rest of the article. Another problem that comes up is kind of conceptual. It's about loss of context. So picture being zoomed far into a map of a city you're not really familiar with, and then you do a lot of panning. For example, if you're following street directions and you want to see what else is in the area. Eventually you can lose context in that you'll know you're still, for example, in Montreal, but you can lose a sense of which part of Montreal you're in relative to the rest of the city or relative to where you started. And then another issue to think about is how to use overlays. So when you include desktop-sized elements like legends or layer selectors or information panels, and just port them over to mobile, they can end up covering too much of the map beneath. And the last common issue that we encountered came up because the map we were building was interactive. So when you are making an interactive map, your markers are essentially buttons. And there are conventional interface design guidelines that specify that buttons should have a minimum size to accommodate the fact that you're touching them with a finger instead of a mouse pointer. And we are in a situation these days where there are many different screen resolutions and many different operating systems. So the minimum recommended mobile button sizes are dealt with differently depending on which setup you're targeting. For example, Windows phones set out their guidelines in millimeters. Apple uses points. When I was working on this map, I was using a really old iPhone. Apple says tappable areas should be 44 by 44 points minimum. The phone I had was so old that 1 point equaled 1 pixel. But more recent phones are at higher resolutions, so the pixel dimensions are going to be greater. So the point is that you should check the interface design guidelines for your target audience, but the smallest recommended size that I found was 26 pixels, which is the red area that you can see in the screenshot. And we were encountering a problem because even at that 26 pixel size, and even if you are zoomed far into your map and you have marker overlap sets of false, you could still get into this situation where more than one feature is falling into that minimum tappable area, so you're clicking on more than one feature at a time when you don't really want to be. So this kind of brings up another point that's kind of important to notice here. This is an example of why cartography should be considered in conjunction with interface design and not separately, because you could see how elements like marker size and graphics affect how the interface is able to be used when we consider that minimum tappable area. Okay. And then when we do start thinking about the more traditional cartography side of things, there are a few basic elements to consider. Markers are only one of them. Like with any map, we need to consider projection. When I was researching this, I did find that there's a debate about whether it's more appropriate to use equal area versus conformal, but the consensus by larger services is to use conformal. But it depends on your use case, whether it's more important to preserve area or to preserve shape and angle. So for example, if you want your map to look accurate when someone's looking at it on their phone and trying to find walking directions, you should use a conformal projection, because there's going to be less shape distortion when you're looking at that smaller area. So, for example, a city block you're viewing will look rectangular instead of skewed. And if the map shows a turn at a certain angle, that angle is more recognizable in real life. And north is always up. For fonts, so guidelines say that fonts should be 14 to 16 pixels, 10 to 12 pixels at the smallest. And technically, actually, you should be using rems based on a % root font size when you're, instead of pixel sizes when you're coding these, but that's like a whole other 15-minute talk. So I actually don't take that 14 to 16 pixel size or 10 to 12 pixel size as a set in stone rule, because I think it's more of a judgment call based on the type of font you're using. Because a font's X height and spacing also affects how readable it is at a certain size. So I do generally aim for 14 to 16 pixel fonts, and I would try to use fonts with taller X heights. If I'm using serifs, I try to make sure that they're strong enough to visually keep their shape and not disappear at small sizes. And widening the tracking can make it more legible at small sizes. So for example, you could see that source is much more, even though the screenshot's kind of fuzzy, you could see that source is much more readable than Didot. Didot's serifs, totally get lost when it's at a small map label size. For images, so for marker graphics, the best practice I have found is to design using a minimum amount of icon elements. So if you notice, out of these two icons, the more complicated building details are lost at a small size. I know this is like a fuzzy screenshot, but even if you are using something vector, an SVG, you still will kind of start to lose detail when you get to map marker size if you're using a more complicated icon. A second tip is to make the element shapes as simple as possible and leave a lot of white space between them. And when we choose colors, more contrast between foreground and background is better, especially so we can make our maps more accessible to people with low vision. So these are the basic design considerations for any web map, but really what I want to show you is that there's another major consideration for responsive map cartography, and that is, should your thematic map type change? So this is the responsive map prototype I built. It's a map of Montreal parking signs. And even though you're seeing clusters on mobile and individual points on desktop, this is the same map. It has one code base. And in the mobile side, you can see it uses buttons to solve some of those problems we saw before. So we get around that accidental scrolling issue by having the pan and drag and zoom functions disabled in this map until you click on this 4 arrow button at the bottom. Context loss is solved with that home button. When it's clicked on, the map is reset to its original center coordinates and zoom level. And this is only one prototype and one way to solve this. There are other methods too. For example, you can use insets. I didn't in this particular case because I didn't want it to take up that much screen real estate, but there are other options. The problem of legends taking up too much screen real estate was solved with that 4th button down, which toggles the legend on and off. And you'll see we also use larger fonts and a thinner legend on mobile compared to the desktop one, so it's more legible and it's taking up a little bit less screen space. And this map is interactive, so when you click on a point marker, you see the sign's description in the desktop version, but this interactivity is what prompted the cluster solution, because if you just, kind of ported that desktop map as is over to a mobile screen, you run into that issue of accidentally clicking on more than one marker at a time, even if you're zoomed far into the map, and just making all of the markers 26 pixels wide wasn't a solution here, because even at a large scale, many overlaps too closely to be selectable anyway. So the solution that we came up with was to aggregate these individual points into clusters based on location. And another part of that was that we had to display all of the unique sign descriptions that each cluster represents in a pop-up window. So like I said, this is a prototype and just one version of a solution, but the main thing here that I want to show you is how you can change the map theme, since that's how we got around that interactivity issue. And the way we did it in this map was to use window functions. So a window object represents a browser window that contains a document, like this map's HTML document, and it has methods that you can use to detect the browser window size and when it changes. You can use these with every major browser. So keeping in mind that our maps data layer is made from a SQL request that gets styled, you can use window functions that trigger other JavaScript functions that will set that SQL and set that CARTO CSS. So in this map, we were looking for a screen width of 550 pixels or less, which would indicate the person's viewing it on a smaller screen like a mobile phone. And when that was found via window functions, we knew to set a SQL query that generated those clusters, and then we applied feature styles by cluster bucket. But if a screen size over 550 pixels was found, like if a person is viewing the map on a desktop or a landscape tablet, we set the query to just be a simple selection and set simple point styles. We also use these window functions to trigger the addition of those mobile buttons we saw, and the addition of the proper pop-up info window templates, since those were built from HTML. And really quickly, these are what the queries looked like. So we started off by creating variables to represent each type of query, point and cluster. When the window function detects that the screen width matches 550 pixels or less, it runs this JavaScript function at the bottom here that generates cluster SQL. And then it uses another JavaScript function to create the data layer with the result of that query and the cluster styles. So in this cluster function, I was using an older CARTO editor algorithm, but you could really plug in any cluster query that you would like here. And if the window function detects that the screen width is larger than 550 pixels, it just uses a simple selection of that whole parking signs table, which is named signalization RDTT at the top there, without clustering to make that point map we saw. So just really quickly, one last note about the styling. So let me go back up to the map. Usually I try to change styles by zoom level, but I did not do that in the cluster version of this map because 26 pixels always has to be that minimum size for the smallest cluster bin. And I sized the markers for the other bins based on a scale factor, so I was always scaling up from that 26 pixel width. Since there were 5 bins to style, you could see that using that method, the top bin's markers are really big already, so I didn't want to go larger than that. So this is something that's probably up for discussion, but in this case I thought it was better not to style by zoom level since the markers can only get larger. And that's it.